data-rich environment. So let's welcome Professor Denis.
Hi, actually, change of plans, right? We have notified, right, that the presenter will actually be my co-author, Lim Kai-jo. So he actually knows better what's going on with the paper. So he will present the slides, but we are here both for questions.
Thank you, Denis.
Kai-jo, the floor is yours.
Yeah, is the slide showing okay? Yeah, okay.
Yes.
Good evening, everyone. I'm Kai-jo, and together with Denis, we are here to present our paper, Inflation and Output Growth Forecasting in a Data-Rich Environment Using Extreme Gradient Boosted Trees with Online Learning. So for this paper, we forecasted inflation and output growth. Inflation forecast is important because it anchors the inflationary expectation for all economic agents, and it helps the central bank form an optimal policy. For output growth forecast is important as it acts as a proxy for GDP growth. So there are several difficulties in macro forecasting. Firstly, it's very difficult to beat the naive benchmark, such as the random walk model. There has been some promising full sample performance using more complicated statistical models. But it has been found that most models perform well only because of the volatile pre-grade moderation period. Moreover, most predictors were found to have lost their predictive content after the grade moderation around the 1980s. There has been past attempts in using machine learning models in macro forecasting. Earlier attempts often focused on linear regularized methods. More recently, there's been application of more complicated models such as random forest and gradient boosting trees. However, it has been found that most off-the-shelf machine learning models led to lackluster results. Moreover, there's often a focus on results rather than interpretation. So this paper has two aspects. First is the forecasting performance. We apply XGB model on the data-rich macro forecasting environment. And we done this using a last log pseudo out of sample forecasting experiment. We then modify the XGB algorithm to better suit the persistence in the macroeconomic data. We use adaptive trees and a novel online learning of n-trees algorithm. We also characterize the XGB temporal performance across time using a multi-block POOS experiment. The second aspect is uncovering new economic stylized text. We unravel the black box using sharp feature importance, where we found that the predictive contents of predictors did not actually drop after the grade moderation, and that inflation persistence was mainly from inherited rather than intrinsic sources. So for the benchmark model, we have the random walk, autoregressive, and autoregressive complemented with PCA. For the machine learning models, we have the XGB model, the XGB, the standard off-the-shelf model, XGB-HB, and our online learning variants, XGB random walk and XGB combination. We also compare XGB to another popular machine learning model, random forest. So here are the three statistical models: the random walk, the autoregressive, and the autoregressive with factors estimated via PCA. For the XGB model, the XGB comprises of many decision trees that are trained sequentially. For the first boosting iteration, a single decision tree is trained. For the second iteration, the next tree is trained on the previous round residue or error. And this continues on for many iterations until we hit the total number of trees or n3. For XGB, it's very important that we control the complexity of the model. And this can be done by controlling the total number of trees, n3. N3 is often determined by some validation scheme. For example, we can split the data set into a training and validation data set. We train the model on the training data set. As we add more trees, the training loss starts to decrease. The validation loss also decreases as the model fits the training data better. However, if we add too much trees, the model becomes too complicated and we start to overfit to the noise in the training data. So for the standard XGB model, the same entry value is used for the entire test window. However, for macro forecasting, there are structural changes across time that causes variation in the optimal entry. And therefore, using the same entry value for the entire test set is often suboptimal. Our online learning algorithm uses a second forecasting problem to forecast the optimal entry to use for each time step. So we'll cover more on this later. So for this paper, we use the FredMD dataset, which has 128 different macro indicators from 8 broad groups. The FredMD dataset is often used as a benchmark to compare high-dimensional forecasting methods. For output growth forecast, we measure the first log difference of industrial production. For inflation forecast, we use the first and second log difference of CPI or items. It is widely debated if the first or second log difference is preferable, and we investigate both to see which method works better for machine learning models. So for the last block pseudo out of sample forecasting experiment, the goal is to estimate the general model performance. For the multi-block POOS, the aim is to investigate the temporal variations in the model performance. For the last block POS, we split the available data into an estimation set and a test set. The estimation set is used for hyperparameter tuning, such as determining the optimal entry to use. After the optimal hyperparameters is determined, we perform a rolling window direct each step ahead forecast on the test set. We can then calculate and compare different model performance. For the multi-block POS, it's mostly similar, except that the estimation data set is much shorter at 10 years. The hyperparameters is retuned every 5th year. We can calculate the loss for different time horizons. For example, pre-grade moderation versus grade moderation. So covering the last block POS, we first find that inflation forecasting in first difference is better for all models and all H steps ahead. This can be seen by comparing the first row and the second row. Moreover, the difference between first and second log difference is more important for machine learning methods. The machine learning methods are the bars in green. So this implies that second differencing of inflation might be over-differencing, leading to a loss of memory, where more complicated machine learning models will find it harder to perform. Next, we also observe that machine learning methods perform better for longer horizons. For output growth forecast, machine learning methods only outperform for the 24 months ahead forecast. And for the inflation forecast, machine learning methods outperform for the 3, 6, 12, and 24 months ahead forecast. We also observe that XGB and random forest has mostly similar performance except for longer time horizons, where the XGB model outperforms. Okay, now we cover more detail on our online learning algorithm. So zooming in on how we perform the hyperparameter tuning, the estimation set is split into a training and validation set, where we train on the training set and we estimate the number of tree entry to use based on the validation error. However, there's assumption that the validation and test set has a similar data distribution. For typical machine learning application, it's easy to ensure that this assumption is met. But in macro forecasting, there's likely to have structural changes across time, where using the same entry for the entire test set is suboptimal. Here is a plot for the Oracle entry, which represents the optimal entry to use for each time step being forecasted. And the optimal entry is clearly not constant across time. The Oracle entry can be treated as a secondary time series to be forecasted each step ahead. So for example, assuming we want to forecast inflation and we are at 2009 third month, we use the available data to train the XGB model. We also use the Oracle entry time series to train an online learning model. We then use the online learning model to predict what is the entry we should use 2 years ahead in 2011 third month. We then use our XGB model to perform the inflation forecast. The difference is that the entry that we use is based on the online learning model. We have tried many different online learning models, and what works the best is a simple random walk model, where the t plus h forecast is simply the value at time t. So now we take a closer look at the learning curves across time. So we see in the first period, from 2005 to 2009, the learning curve has a similar shape, which we term as LC1. So this is where, as we add more entries, the model performance improves very quickly, where the model, where the training loss decreases very quickly, and it shallows out. And here the optimal entry is often large, greater than 100. There are some fluctuations in the Oracle entry, but because the learning curve is quite shallow at those regions, the exact value of the entry predicted is not that important, as long as the model predicts a value greater than 100. We then see a next distinct block from 2009 to 2011, where the learning curves has a shape LC2, where there's a steep drop in the model loss, followed by a steep increase. Here, the optimal entry is usually small, less than 20. We then see that there are distinct blocks which alternate between LC1 and LC2. There are high persistence within the distinct block, where the intra-block difference is very small. The transition between the blocks is very rapid. Therefore, the overall entry time series is very persistent. The online learning algorithm can exploit this and improve upon the naive constant XGB model, where the same entry is used for the entire window. So XGB-C is the forecast combination of the XGB random walk and the XGB, the standard XGB. The XGB combination is more robust and has more consistent performance across all H-step ahead forecasts. For output growth forecast, online learning is most useful for the 6 and 12 months ahead forecast. For inflation forecast, the online learning model is better for the 3 and 6 months ahead forecast, and has similar performance for other H-step ahead forecasts. So moving on to the temporal variations. In the introduction, we mentioned that models tend to have good full sample performance, but most of those performance gains were wiped out after the great moderation. The question is, does this apply to XGB too? So here we have two plots, which is the ratio of the model's loss after the great moderation divided by the pre-great moderation period. We see that excluding the autoregressive model, the XGB generally has a smaller ratio, which implies that performance did not decrease as much due to the great moderation. And therefore, XGB is more robust to structural changes compared to the other models. We also mentioned that the predictive contents of predictors decrease after the great moderation. The past study has shown this through a one-time reversal test for many predictors across the board, and found that around the 1980s, all those predictors lost their significance and were less useful for forecasting. To see if this is true for XGB too, we train an XGB model and we unravel the black box using sharp feature importance. We then perform a temporal analysis of those using the sharp values. So the sharp value explains the marginal contribution of each predictor that results in the final forecast for each time step. For example, the 2020 fifth month forecast for inflation is negative 0.65. The sharp value decomposes this forecasted value into the base value 1.4 and the sum of all sharp values from all predictors. So predictors with positive sharp values pushes the inflation forecast up, and predictors with negative sharp values pushes the inflation forecast down. We can take it one step further and calculate how important groups of predictors are using the sharp proportion. For example, we can calculate the sharp proportion for the group of predictors, the stock market, by summing up the absolute sharp values of all stock market predictors divided by the sum of all absolute sharp values. So for example, if a group has near zero Sharp proportion, it means that it has almost no influence on inflation forecast. And therefore, we can conclude that that group is less important. So here we have our 8 groups from the FRAC-MD dataset, and we have one extra one, which is AR, the autoregressive terms. So looking at the 1980s, we see that the AR Sharp proportion in blue is always small. If the predictive content of external predictors did decrease after the 1980s, we should see that the autoregressive term should increase. However, this is not the case. The AR Sharp proportion did not rise significantly. And therefore, we can conclude that the external driving forces or other predictors are still significant even after the great moderation. So why is this different from past studies? So past study used a simple auto-distributed lag model with only one additional predictor, which might be too parsimonious. The XGB is more flexible and can choose which predictors are important for different time periods. This allows for non-linear interaction effects between multiple predictors, which allows predictors as a whole to maintain their predictive content. And the last issue we examine is inflation persistence. So inflation persistence can be broken down to 2 sources using the hybrid New Keynesian-Phillips curve. One is the inherited persistence, where inflation is influenced by external driving variables. The second is intrinsic persistence, where inflation is inherently persistent due to the lag terms or the AL terms. So we can determine which persistence is more important by comparing the value of their coefficients. So there are smaller coefficients on the external driving variables, gamma, compared to the larger coefficient on the lag variables, mu. This implies that intrinsic inflation is more important than inherited persistence based on this model. Comparing to XGB, we see that the opposite is true. The AL Sharp proportion in blue is always a much smaller fraction compared to the external driving forces. This shows that the external driving forces has a larger influence on inflation forecasts. Unlike the Phillips curve model, this suggests that inherited persistence is actually more important. So why is this finding significant? So central bank actions influences inflation persistence through external driving forces. If inherited persistence is unimportant, this means that central bank actions cannot influence inflation persistence. But this is unlikely to be the case. It's more likely that current models cannot map policy actions onto inflation correctly. With XGB, we can show that external driving forces are actually, in fact, more important. So in conclusion, we introduced a novel online learning algorithm that boosted XGB performance. We show that XGB is a viable macro forecasting tool, especially for longer horizons, and that XGB can be more robust to performance changes due to the great moderation. And lastly, we uncovered the black box using sharp feature importance and show that predictive content of predictors did not actually drop after the great moderation, and that inflation persistence might be largely from inherited rather than intrinsic persistence. Okay, so thank you. Any questions and suggestions are welcome.
Okay, let's thank the speaker. So any questions from audience, please?
Yeah, hi. Thanks for the talk. It's far from my field, so my question might be naive, but why do you want to use XGB? Why not use other models? The neural, you could in principle try neural networks or other stuff, right? I'm trying to understand why is this the right algorithm for these classes of problems?
Okay.
My question.
Oh, I guess I can take this question. So the reason why we sort of pay a lot of attention to XGB here, right, is that if we come back to the literature that Kaijo introduced in the first couple of slides, right, there has already been quite comprehensive studies of standard off-the-shelf machine learning methods, right? For example, Medeiros and co-authors, and more recently Coulomb, Marcellino, and other co-authors. And so the the kind of finding from that literature, right, is they tried a lot of machine learning methods, and the finding was that nothing beat random forest, right? That this is why we also focus a lot on the random forest, that the finding in the macroeconomic forecasting literature is that whatever you do lasso with various tweaks, you do neural network, you do whatever it is that you like from the kind of a standard machine learning menu. Nothing seems to beat random forest across multiple horizons. In fact, those guys also tried XGB on default settings, right? So the kind of the motivation was that XGB seems to perform really well in machine learning competitions, across fields. And so why didn't it sort of outperform in the macroeconomic context, right? And so basically, this is what this paper trying to investigate, right? Maybe what are the correct tweaks, right, for this method to shine. And so it seems like this online learning scheme is really kind of helping XGB realize its potential, right? So it's really the focus here is building on the findings of the previous literature, right? That sort of established that random forest is a very hard to beat benchmark here, right? We provide a method that actually beats it.
Thanks.
Any other questions? How about audience from online?
Yeah, so I have one question. Can I ask?
Sure.
So what is the data you use here? So I mean, like, are these after the revisions, or are these the first unknowns? The inflation. As we know, like, later they correct the numbers, etc. But if you really do the forecasting model, so you should use the first unknowns.
Yeah, so that's a great question. And that's a tricky one to answer in practice. So I think, so we use the FredMD data as they're available on the St. Louis Fed website. I think these are probably revised data. I totally I'm totally on board with your point that if you are really forecasting in real life, right? So you are facing the first release for your most recent data points, right? And your less recent data points may be already revised, but still may be revised, right? So there is this revision kind of issue. We haven't controlled for that because I think it's primarily very difficult to assemble this large data set across different vintages across the entire time period. So in that respect, the findings should be taken with a pinch of salt, right? So this is probably not what's going to happen to your predictions in practice. You're probably going to predict a little bit worse. In sort of in a defensive argument, right? So the existing literature does the same. So if we benchmark ourselves against the existing literature, it's not like we're being unfair comparing to the existing literature. And I would say that these revision issues are more prevalent for some variables like GDP, or industrial production, rather than inflation. Inflation tends to be, I think, revised a bit less than GDP, but GDP really suffers from huge revisions. And especially during recessions. So that's definitely one point where applied forecasters should be careful. Yeah.
But you could easily do, easily, just, crawling window basis, now you could look at, use the, whatever is unknown first and, just check, in real time, so.
Yeah, maybe that's an exercise for another paper because it's just the sheer amount of data knitting that would involve would be quite intense, right? Because you would need to update at every point in time, you need to update for all the revisions that happened for each data point. But that's an interesting, how much the results would actually change. Yeah, I think people doing nowcasting, they are very careful about that. So I think that's if we're talking about especially things like nowcasting, that it's definitely a point to look out for. Yeah, so this could be taken as, if we had ideal data, right, then what could we do? It's probably going to be, the relative performance probably going to be the same, right? But the absolute mean squared error would probably be lower. Sorry,
I'm
higher.
just
higher.
I'm just thinking practitioners, you know,
Yeah,
so
yeah,
I
yeah.
want them to use, you know, your
Yeah.
model. And,
So from the practical point of view, I would think that the interesting point here is the ranking of the methods. I don't think the ranking would change, but the actual values of the errors would change definitely.
Okay, thank you.
Any more questions? Okay, if there's no question, let's thank the speakers.